Welcome to the Altruistic Libertarian, advocate for a genuinely free society. I'm Anthony Wheeler, and today we continue a case study on our deadly highways, including a potential solution. It remains impossible to predict precisely how the transportation system would have developed absent government intervention, other than to confidently assert it would have been far safer, faster, more cost-effective than what exists today. Same goes for the future, should an enlightened society commit itself to ridding itself of such a monstrously destructive system. What can be provided, however, is an analogy that closely matches the transportation industry, one that serves as a meaningful test case. Telecommunications are not all that different from transportation. They both transfer something from one place to another. The former, voice and data. The latter, people and things. Early in the 20th century, AT&T was granted a monopoly to provide voice telephone services in the United States. This made it illegal for anyone else to offer such service to the public. This monopoly lasted until 1984, when AT&T was broken up into 8 entities, AT&T and 7 regional Bell operating companies, or RBOCs. AT&T would now compete to provide long-distance service, MCI and Sprint their main competitors, while the RBOCs would remain local monopolies. In addition to the RBOCs, hundreds, if not thousands, of smaller local telephone companies maintained their monopoly and the subsidies that went with it. Legislation in 1996 paved the way to remove the remaining barriers to competition in the industry, allowing anyone to provide local services in most locations and allowing the former RBOCs to provide long-distance service once certain requirements were met. In 2005, SBC, formerly one of the 7 RBOCs, morphed now into a massive telecommunications conglomeration, purchased AT&T, and while keeping the brand name, absorbed the remaining bits of the former monopoly so that the original master no longer exists. When I joined AT in 1990, the company was almost desperate, attempting to restructure and shed costs. Sprint had just dropped the pin, emphasizing the quality of their phone service. All digital, they proclaimed, leaving out the small detail that the majority of their traffic was carried on AT&T's network. That's how Sprint began their business, by reselling AT&T service, slowly transitioning to their own network as they completed their build-out. They insisted, though, as AT&T's largest reseller, that all their traffic be carried only on digital transport, leaving much of AT&T's customers to suffer from aging analog circuits. AT&T had grown massive and inefficient through the decades of complacency brought about by serving a captive market. When I arrived, a rare college hire, I worked for the Network Services Division, that part of AT&T that managed the core network. NSD had just collapsed 7 regional control centers into 2, one in Denver and another in Conyers, Georgia, a small town about 20 miles east of Atlanta. The centers housed a network operations center, performed core provisioning and maintenance, and issued work orders to the various central offices around the country. Massive downsizing, layoffs, and radical system upgrades accompanied centralization, both of which were considered fundamentally important to the long-term financial viability of the company. To make the comparison between the continued existence of a killing highway system and the evolution of telecommunications, and how the recent history of the latter can provide insight into the potential future of the former, it's necessary to understand the basics of traditional telephony. This will be referred to as a circuit switch network. The circuit switch network evolved directly from the very first telephone networks. Recall scenes from old movies. Someone cranks the ringer on the side of their old phone, and an operator somewhere nearby picks up the line. "Connect me to Mrs. Smith," the caller, let's call him Carl, may say. The operator nods and takes a cord and plugs it into Mrs. Smith's line, completing a direct metal path between the 2 phones. When Mrs. Smith picks up her phone, the 2 parties can talk. Now imagine that Carl in San Diego wants to call Tom in Alpine. To do that, he rings the operator in San Diego, and she seizes a trunk to the operator in Alpine and requests the call be connected to Tom's line. Once the operator makes the connection, there is now a physical connection between Carl in San Diego and Tom in Alpine. Note that a line is exclusively usable by one phone, whereas trunks contain multiple circuits that can be used and reused in any combination of lines. The next major step in our story is to replace the human operator with a switch. The network doesn't really change. The pre-1996 US telephone network would look something like this, showing only one long-distance provider. The first switches were developed or deployed before the monopoly was established in 1913 and remained the core of the network in 1996. Originally, mechanical switches were deployed and later converted to electronic and eventually digital switches. These advances improved quality, call setup time, and eventually added new features, call waiting, voicemail, caller ID for instance, but in essence maintained the same fundamental architecture and capability as the network originally built in the early 1900s. This would be analogous to the highway system adding stoplights, freeways, on-ramps, and seatbelts in cars. The actual infrastructure, the roads, doesn't change. The circuit switch network was designed and perfected to carry voice conversations and little else. All the telecommunications networks in service in 1996 were of this design, all of them using the same circuit switch technology that was decades old. In a traditional circuit switch network, anytime a call is made, the actual physical electronic path must be established and maintained throughout the duration of the call. As can be seen in this diagram, these network resources are utilized during the duration of the call. The path itself operates at a fixed maximum of 64 kilobits per second. While this works perfectly for a telephone call, the capacity of this electronic link is completely inadequate for most other uses. Video, for example, or the transmission of large amounts of data. The development and stagnation of the telecommunications infrastructure in the U.S. up until 1996 is directly comparable to the state of the transportation infrastructure today. I would even go so far as to suggest that the upgrade from analog to digital in telecommunications comparable to building out the federal highway system beginning in the mid-50s. Both changes made the systems incrementally better without changing the underlying architecture. Both represent simple evolutionary steps within the constrained and unnatural course of their history. Most people believe that the highway system in the U.S. is a necessary and right if they consider the question at all. They remain unaware that superior alternatives exist in terms of flexibility, safety, cost, or convenience. As an alternative, all they can imagine is some form of public transportation, buses, trains, and they blanch at the possibility of depending on either to get them from one place to another. They want their own car and the freedom that goes with it. This can be collectively characterized as a failure of imagination. Prior to 1996, the same people had no idea what possibilities existed within telecommunications, what capabilities would become common within a mere 20 years. To fully appreciate the genuine nature of that industrial revolution within telecommunications and to gain an insight into how something comparable could happen in transportation, it's important to understand what actually changed. The Telecom Act of 1996 eliminated most of the remaining legal limitations within telecommunications, allowing radical new capabilities to be developed. The key to this revolution was the migration from traditional circuit switch network architecture, one that was designed and perfected for voice communications, to data networks. Data networks have existed for a long time. The signaling network that provided call setup in the traditional circuit switch network is an overlay network that uses data packets to communicate between the various network elements. This packet network arranges the path the call will eventually take, checking each switch for capacity in order to establish the dedicated circuit. Ironically, the overlay network has in essence become the network of today, as everything is migrating towards packet/data networks. Various data protocols exist, but have one thing in common. They all structure the digital content in discrete packets. Sometimes called frames, frame relay, or cells, an ATM, the concept is the same. Each discrete packet has information regarding destination, error checking, and other variables, along with an actual payload of digital information. The payload can be anything, part of a voice conversation, a picture, music, video, email, financial records, and spreadsheets. Anything that can be made digital can be transmitted within a data network. Instead of a network diagram, the best way I can describe a packet network is to provide a specific example. This is what a packet looks like in IP. That stands for Internet Protocol, which is the most common. The first 20 bytes is the header. A byte is an 8-character digital word that can render unique values from 0 to 255. You can see that the header consists of various sections. Type of service is particularly important because that field will enable telephone service. A packet identified as part of an ongoing telephone call will get prioritized as it enters a router, putting it at the front of the line for processing. This improves quality and reduces the latency during an actual conversation. The header checksum provides error checking. If the numbers don't match appropriately, the router knows the packet has suffered an error. The source IP address and the destination IP address indicate where the packet originated and where it is headed. The data section can be various lengths and will include a digital portion of a voice call, an email, a stream video, any digital content whatsoever. In a circuit switch network, the dedicated path is established prior to any content transmitted, a conversation say. Both ends are already set, so the content doesn't need addressing information. It can only go one place. In contrast, when a packet is sent into a data network, it must contain unique address, so each router can determine where to send it. The packet will likely transit several routers prior to reaching its destination. Once there, it will be assembled within the proper order, made necessary by the fact that the various packets that made up a discrete message may arrive out of order as they may have traveled the network along different paths. Error correction marks another difference between a data network and a circuit switch network. In traditional data networks, the accuracy of the data is paramount. Charging a credit card, for instance, you don't want the wrong numbers to be sent or received. To prevent errors that inevitably occur, most data protocols provide error detection. If a string of data packets shows errors, the receiving router requests the sending router to resend the data. That way, the precise information originally sent will ultimately be received at the far end. If the transmission is delayed a few seconds or even longer, it won't matter. In a traditional voice network, on the other hand, such delays would cause unacceptable latency, making a conversation difficult to conduct, whereas occasional errors in the bit stream would rarely be even noticed. This is one of the main reasons that data networks were not seriously considered prior to 1996 for voice communications, as the voice quality was generally fairly low. But even more important, voice communications was a massive industry, one that would have successfully blocked any voice service delivered by data networks alone, absent its deregulation. A data architecture has two major advantages over a circuit switch network, one of which would prove decisive. In the first place, a packet data architecture is far more efficient using the same network resources. In a circuit switch phone call, the entire path is dedicated as long as the call takes place. The only time content is delivered, however, is when somebody actually speaks. Any dead time means unused network resources. In a packet network, the same phone call only sends data to the network when somebody speaks. The second difference is simply this. Where a circuit switch network will support excellent quality phone service and extremely low capacity data transmission, maximum of 64 kilobits per second, it can do nothing else. A data network, on the other hand, has no architectural limits. Virtually unlimited bandwidth can be transmitted, with any content delivered at speeds unimagined just a few decades ago. Movies, phone calls, music, anything. Perhaps another comparison would be helpful. Prior to 1990 or so, the only routine way to produce a letter quality document was to use a typewriter. When computers came into common use in the 60s and 70s, dot matrix printers were common. The same dot matrix technology was used initially when PCs became prominent. Sure, you could create a document using a word processor or a spreadsheet, but the only way to create a hard copy was by using a dot matrix printer. When HP came out with the first laser printer, this changed. With the new printer, high-quality documents could now be produced using a PC and printer. Not only that, PCs could adjust the font styles and size in an instant, whereas most typewriters only had one. Finally, a user could do everything a PC could do, plus everything a typewriter could do, yet far more efficiently. It wasn't long before typewriters disappeared from everywhere except museums. In time, circuit switch networks will go the way of typewriters for exactly the same reasons. The conversion from a circuit switched architecture to a data architecture required building entirely new networks, establishing new protocols and standards, developing new technology and equipment, and creating new business models. The results have been astounding. New products and services and information sources undreamed of just a few short decades ago have now become common. Smartphones with high-speed web access, texting, downloading music, YouTube channels, watching movies on a tablet, Skyping across the world, shopping for anything online, and reading news and reviews in real time. And it just struck me, this entire channel that I'm recording right now would not have been possible 20 years ago. And costs have plummeted. It costs less today for unlimited local and long-distance telephone service for a month than what a single 4-minute call between LA and New York City cost in 1980. One short phone call cost more just a few decades ago than a month's worth of unlimited service today. None of these things would exist today if the government hadn't finally removed legal barriers in the telecommunications industry. A comparable transformation would take place in transportation if the government got out of the transportation business. One of the least understood consequences of government intervention is the opportunity cost of what might have taken place absent the intervention. People are so comfortable with current circumstances that they don't miss what they don't know. Had AT&T maintained its monopoly and we continued to pay for every minute of long distance we used and accumulated large monthly bills, we wouldn't know that something better was even possible, let alone how such alternatives might be brought about. As for ground transportation, little has changed or improved in decades. The roads are not much safer, faster, or cheaper to use, the three criteria a private operator might consider. In fact, between 1974 and 1987, the national speed limit was lowered to 55 miles per hour, a major step back in terms of effective transportation. Consider the history of the common traffic light. Invented in 1912, the automatic traffic light was first installed in 1923 and hasn't changed much since. Many traffic lights now have sensors, and in some stretches, the lights are coordinated with fixed algorithms. Incremental improvement at best. The next significant advance was the modern freeway. It came into existence with the Federal Aid Highway Act of 1956. This innovation allowed much faster and more efficient transportation between cities and generally within, and until in recent decades when the growth of traffic greatly exceeded the infrastructure. Commutes in many major cities have grown increasingly problematic, and traffic accidents can stall commutes for hours at a time. Like any government-owned institution, education, Social Security, there are no incentives or motivation to change. Even if a municipality wished to research, design, and implement a transportation solution that was safer, faster, and/or cheaper, they wouldn't be able to fund such a project, and if they did fund it, wouldn't receive any benefit from deploying it. Within that municipality, transportation alternatives do not exist, so improving the one that they have doesn't benefit any of the decision makers. They remain in office or on the payroll regardless. Incremental solutions for improving traffic have been deployed in a few cities. For example, for any given stretch of city streets currently managed by traffic lights, sensors are placed that monitor traffic within the entire area. Algorithms are developed to dynamically maximize traffic flow and minimize delays. Traffic signals vary in length and in a coordinated fashion depending on the results of those algorithms. An additional feature provides priority vehicles with the quickest clearance. Obvious cases would be ambulances and police vehicles, but the list can be expanded to others. This is the extent of changes made on city surface streets in almost 100 years. Ground transportation generally costs as much, if not much more, per traveled mile, and has hardly been made any faster or safer in that time. Well, that concludes our show for today and our overview of the deadly highways. In the next episode, we will consider a possible solution, the traffic panacea proposal. Until then, peace.